Good morning, everybody. Dr. Finzi and my colleague from Lonza have covered a lot of the things that are in my slides, and they covered it in Portuguese. So when we hit slides where there's an overlap, I will try to slide by them fairly quickly in the interest of time. This one? Aqui. So my objective this morning is to review sources of microbial contamination, the impact of microbial contamination on the fluids, and talk about some strategies to minimize and control microbial contamination. As you've already heard, water is the biggest component of the fluid, and even if it's treated, it's not sterile. So it's a major source of contamination. Dirt, many sources. The air, the metal being worked, floors, all sources of contamination for the fluid. The workers themselves can be part of a problem. And very important, in all systems, when systems are cleaned out, unless a system is properly cleaned and treated before recharging with fresh fluid, the spoiled fluid is going to introduce contamination into the fresh charge. If we look at the published literature, there's a whole range of organisms that have been isolated from fluids. There's data going back to the mid-1950s through to more modern genetic-based techniques. But what we see of the organisms are predominantly gram-negatives, particularly things like Pseudomonas and Proteus, Klebsiella. And as I like to say, the only thing remarkable about these things is there's nothing remarkable. In other industrial spoilage situations, we see exactly the same organisms. Give you a little bit of idea of what these look like. This is a scanning electron microscope photograph of Pseudomonas. And they're very small, typically 1 to 2 microns. And in diameter, even less, maybe 0.3 microns. So it's not unusual to have bacterial counts that may be as high as 10 to the 10. And we now know, using genetic methods, we're probably only culturing, when we do plate counts or dip slides, about 1% of the organisms that are actually there. So the counts are actually much higher than we get. If we look at the fungi that we find in metalworking fluids, the list is smaller. Fusarium and acremonium are very common, and you also get some yeasts, including things like Candida. Everybody hear me now? And here's some typical photomicrographs of that is Fusarium, very typical canoe-shaped conidia. This is acremonium. See how they form very dense mats, and when this happens in the field in a fluid, that can cause significant problems. This is Candida. It's not a true yeast, but it does grow by budding, but this one can also grow as a filamentous form. Typical size of most yeast, much bigger than the bacteria, 10 to 40 microns in size. So here you see Pseudomonas together with acremonium, and you see the difference in size. So it's important to understand the difference. So this is why a fluid may be able to tolerate some low bacterial counts, 10 to the 3 to 10 to the 5 is not a huge issue. But if you have 10 to the 3 to 10 to the 5 fungus, that's a big issue. Here's a photograph of a heavily contaminated fluid in the field. So you can see that's the real world. In terms of growth requirements, as we've heard, all these things they need the same as us. They need adequate moisture. If I don't get water, I die. We need a suitable temperature. Typical operating temperatures of 10 to 40 degrees are perfect for these microbes. And we need a suitable food source. And pretty well everything in the fluid can be degraded by one or more types of microorganisms. In terms of growth, most bacteria grow by simple binary fission. 1 divides and becomes 2. 2 divide and become 4. And under ideal conditions, some bacteria can reproduce, in fact, in as little as 8 minutes. So if you assume that they divide every 15 minutes, if you sat down with a piece of paper and did the exercise, after 1 hour you have 8 from 1. After 2 hours you're up to 256. You go out to 8 hours, potentially you have billions. So that's why you can get explosive growth when a system goes out of control. Now, as my colleague from Lonzo talked about the biofilms, although we usually count contamination in the fluid samples, reality is bacteria and fungi generally prefer to grow on surfaces. And the physiological properties of these organisms on surfaces are very different to the free-floating forms. This is a schematic of a biofilm, and they have fairly complex structures. So you can get a number of effects, but as was pointed out, generally they're significantly more resistant to adverse environmental conditions than their planktonic forms, and that includes resistance to antimicrobials. Issues you get: slow penetration. You have a physical barrier, so to penetrate to kill the organisms within lower levels of the biofilm is a challenge. Organisms like Pseudomonas have adaptive mechanisms. They can actually switch on an internal pump and pump against the concentration gradients. So when they sense BIT coming, they can switch on the pump. And that's why they're resistant to BIT, because they're able to switch on this pump. And the science of persisters is something that's really only been understood in the last decade. Persisters are organisms that are basically will survive treatment, and when conditions become favorable, will reestablish a normal population. If you want to learn more about biofilms, there's all sorts of information on the internet, so I'll reference that. If anybody needs a copy of my presentation, you're welcome to it. If we look at how we count microorganisms, there are a number of methods out there. There are some rapid methods based on measuring enzyme activity. There's an older catalase method I used to run into HMB meters. There's a more modern method based on measurement of ATP. And this is an ASTM standard method. And there is a modification which will be published in the next few months, which will differentiate between fungal ATP and bacterial ATP. But reality is, in practice, most monitoring is still done by dip slides. And a typical dip slide has two surfaces. One side measures bacteria, and the other side measures fungi. So you simply dip the slide in the metalworking fluid, keep it in a warm place for 2 to 3 days, and then compare it against the chart. And that gives you an idea of the levels of contamination. And you use that then to guide your treatment program. Where should you take samples? It's best to always take samples from a point immediately in front of the dirtiest point in the circulating system. Ideally, take it from where the fluid is flowing. So don't sample from a tank or reservoir. It may be easy, but it's not the best way to go. But always take your samples from the same location, so when you chart your results, the comparisons are valid over time. If we look at the effects of microbial attack, some are fairly obvious. If a machine or system is out of control and you shut it down over the weekend, you can get hydrogen sulfide odors. Quite nasty. You can get musty odors, and you may even get ammonia coming off systems from attack of things like MEA, monoethanolamine, and other amines. As the fluid becomes contaminated, the pH drops. And that's a very simple and quick indication of microbial attack. If a plant is monitoring a fluid, and this morning the pH was 8.8 and now it's 8.2, you really don't need to wait for a dip slide. That tells you you've got contamination and it's growing very rapidly. You can also get some selective degradation. Not all the components of the fluid are equally degradable. So, for instance, if you're machining ferrous metals, quite often, if the corrosion inhibitors are attacked, the first indication of attack may be the customer starts complaining of rusting of parts. If you get emulsifiers being attacked, you may start to lose emulsification and fluid stability. We've talked about biofilm. Importantly, biofilm can break loose if it sloughs off a surface, and that may happen because you treat with a biocide. You can get into plugging of nozzles, and you may get into blinding of filters, so you get rapid indexing of filters, and that's because you killed the biofilm. But it can also happen anyway if you don't control the biofilm. But if any of these problems cause you to start to lose cooling or lubrication, then you can get into issues like shorter tool life and poor surface finish on parts. I've been around in this industry a long time. If somebody had asked me as a microbiologist 30 years ago about health risks of bugs in metalworking fluids, I would have really tended to say that the science doesn't support, the published literature doesn't support the health issues. And that's true in relation to infection risks. Organisms like Pseudomonas, and that's a name you've heard quite a few times, in a hospital environment are very serious. People die in hospitals from Pseudomonas infections. But there is no published evidence that Pseudomonas in metalworking fluid causes infections in operators. So it does not appear to be high risk. Sometimes microbes get blamed for dermatitis outbreaks. Bacteria don't cause dermatitis. That's wrong. But they can play an indirect role because, for instance, if you have things like rancid fatty acids from microbial attack, they can promote dermatitis. So it's a consequence of microbial attack, not the microbes themselves. Bacterial endotoxins. Dr. Finzi referred to these fairly briefly. These are the lipopolysaccharide portion of the dead cell wall of gram-negative bacteria. In the hospital field, we call them pathogens, which means they cause fever. They have very well-established effects on the lungs. You can get into changes in cross-shift lung function. You get into airway irritation. All these things are precursors for chronic lung disease. So this is an issue. Most of the science here started to emerge and publish work starting in the late 80s and into the mid-90s. Haven't heard much in recent times. One of the issues is there's no clear level being established on what is safe for metalworking fluid operators. And the fourth thing, which also was referred to by Dr. Finzi, is hypersensitive pneumonitis, which the Europeans call extrinsic allergic alveolitis. This is an overreaction by the immune system to inhalation of an antigen. Importantly, it can become chronic and even fatal. People have died from hypersensitive pneumonitis. In other markets, in other industries, this is known by other names. Farmer's lung disease, bird fancier's lung, mushroom worker's lung. So a lot of different names. And in some of these cases, you'll see farmer's lung disease, we know it's fungal related. Bird fancier's lung is fungal related. Mushroom workers, obviously, it's fungal related. Some of the early published work for metalworking fluid cases suggested a causal link to these non-tuberculous mycobacteria. And there have been animal studies done. They do demonstrate that mycobacteria can cause HP. But there are also some outbreaks of HP that have occurred that have been very well investigated, in which mycobacteria were not found. So it's very clear that there are other causal agents that are involved in some of these outbreaks. Bottom line is metalworking fluids support the growth of other organisms that are known antigens. So it's not as simple as mycobacteria. There is animal studies also that show that endotoxins may be a cofactor. And last but not least is genetics. You have a plant with 300 workers. One person gets HP, or 2 or 3 people. But all the others are okay. So it's like we all react differently. I have to take antihistamines because I'm allergic to pollen. But you may be allergic to animal hair. Okay? Our immune systems react to different things. And individual genetics vary. Important thing to understand is metalworking fluid operator exposure to bacteria and fungi clearly can play a role in potential health risks. So brings you back to controlling microbes is important, not just for keeping the fluid quality where you want, but also for minimizing these potential health effects. And to reinforce what my colleague from Lonza said, preventive maintenance is by far the best way to go. It's much better than reactive maintenance, which is done when a problem occurs. And with preventive maintenance, fluids can be used for extended periods without costly and time-consuming changeouts. There is certainly a global trend of end users saying they want fluids that want no tank-side maintenance or minimal tank-side maintenance. One of the major US automakers considers any additions, not just biocides, but any additions to a fluid to be a fluid failure. So very strict requirements. And we see that in the fluids that we get from our customers to evaluate, to make sure that biocide package is effective. Modern fluids are dramatically more bioresistant than the fluids from even the 1980s. So the fluid selection by the customer has a huge impact on the fluid management requirements and fluid life. Importantly, you're starting off, I know the real world doesn't always allow you to start off with a clean system. Often you have to go in, when you get a new customer, you often have to go in on top of the old fluid. But the reality is, if you really want to get good control, you need to start off with a clean system. So add a system cleaner and a full dose of biocide at the start of the last shift before dumping the old system. Physically remove any contamination on system surfaces, and then rinse the system, ideally with a solution of fresh metal working fluid, or at least with clean water before charging with fresh fluid. The ideal. Some of the things you should be monitoring in terms of managing the system. The pH. If the pH is stable, it's a good indicator the system is under control. The fluid concentration, the odor, the appearance, bacterial counts and fungal counts. These are things you should be doing on a routine basis. Ideally, you want to know the bactericidal levels and the fungicidal levels. That's not practical with small machine applications. With big central systems, it may be more realistic. But also make sure that you're tracking the addition of concentrate, how often, how much, and not just the addition of bactericide or fungicide, but also all other additives. And the amount of water makeup. pH, different fluids have different optimal pH ranges. So as bacteria grow and produce, as we've talked, the pH can fall. So the fluid pH needs to be kept in the recommended range. Some fluids are designed to be used within higher or lower ranges. Control of microbes. When we look at bacterial counts, we report these as usually as colony-forming units per mil, because the assumption is quite often what you're actually counting is a clump of organisms. It's not a true count of the number of organisms there. But we would consider 10 to the 3 as being a system under control, 10 to the 7 as being something that's contaminated, and 10 to the 5 and above really means you need to address the system. Regular scheduled dosing with biocides will keep the counts down and is more cost effective in shock dosing. So again, maintenance versus reactive treatment. Fungal counts are often underestimated. Usually if you're picking up 10 to the 3 fungus or more in a fluid sample, if you go and have a look in the machine or in the system, particularly if you look in the headspace, you'll often find there's very serious fungal contamination. So often be wary about using fungal counts from dip slides. You really need to look periodically. As we've talked about, bacteria and fungi are quite different, so use of bactericides and fungicides, use of both is important for proper fluid management. Over time, levels decrease from chemical interactions. When a bacteria are killed by the biocide, there is some loss of the biocide. And some biocides can also get dragged out with tramp oil. So for any biocide, you have optimal concentrations, and those would be in the manufacturer's technical data sheet and on labels. So try to keep the biocide within those levels, at that level over time. In terms of monitoring biocides, Concentrations can be typically monitored by things like HPLC. For some biocides, there are some fairly simple colorimetric methods that can even be used by the customer in the plant. And at the end of the day, the biocide manufacturers and you supplying your customers, we're resources, so please use them. And obviously, every time you add fresh concentrate, you're also adding in more biocide. So the amount and frequency of makeup will have a significant influence on the need for tank-side treatment. Again, we've talked about some of the indicators. Key indicators are growth on dip slides or agar plates, drop of pH, problems with smell, foaming, corrosion. And with fungi, again, picking them up on dip slides. You can also, if you're having issues with filters being plugged or a sticky filter cake, and if you look in the headspace of the machine, you see them, then they're there. So, and very similar to my colleague from Lonza, here's a table about the common biocides, whether or not they're using concentrates, tank side, and efficacy against bacteria and fungi, and I noticed we were almost perfectly in agreement. So no dramatic differences, so I'll slide right by that. But there are obviously a range of products available. There is an ASTM standard practice for selecting antimicrobial biocides. If you really want to know more about this, it's a good primer because it talks about the decision-making process and what things to consider. Bottom line is every biocide has its strengths and has its weaknesses. And as has been indicated, formaldehyde-based biocides are under significant pressure. There's some regulatory pressure, but you also have unions in some cases that don't want to see certain biocides in plants, and you have end users who have negative lists. One key point to note that, because I talked about endotoxins and the health risks, of all the biocides listed, the only products that have been shown to neutralize endotoxins are triazines, oxazolidines, and glutaraldehyde, so the formaldehyde-based chemistries plus glutaraldehyde. So personally, I have a concern about removing the use of these things because I think there's a potential for exchanging one perceived risk, which the science doesn't support, with a greater risk that has been well demonstrated. So actions to take before adding any biocide: try to identify and control any sources of contamination. If you know the water supply, because we have plants that use well water, for instance, that has contamination in, or river water that's been untreated, try to get them to treat it before it comes in. Control tramp oil in the metalworking fluid. Tramp oil promotes anaerobic conditions, so that's never good. Keep the fluid circulating, because that avoids anaerobic conditions again. Adjust the fluid pH if necessary. Ideally, do that before you add the biocides. All of these products are designed to be toxic against target microorganisms. So to some degree, they're going to have a degree of increased hazard to humans. And the key thing to understand is products that are sold globally, North America, Europe, must have extensive supporting toxicology and environmental data. So, for instance, in the next round of re-registration in the United States, any biocide that has a metalworking claim will require something between $5 and $10 million of additional toxicology data, because we have to do cancer studies and multi-generation reproductive tox studies. So please understand, when somebody says this thing's also a biocide, quote, quote, you should ask them what data they have, because if it's killing organisms, that's what you need to understand, because that's the requirements that we have to meet as biocide suppliers. So I would recommend a good basic precaution is only to use biocides that are truly sold globally. Handle the care is always the first order of business, so read and post safety data sheets, execute a risk management program for handling the product safely. If you know the product is eye corrosive, then where it's being used, there should be appropriate facilities if somebody gets it in the eye. Always wear the recommended personal protective equipment At the end of the day, the safety data sheet is the primary tool for communicating hazards and saying what to do in case of exposure or to minimize risk. Thank you all. Lunch. Thank you.